My name is Zhi from School of Public Health, National University of Singapore. My topic of this talk is new heavy-tail count models in STEM and its applications to the evolution of near skill-free social contact dynamics. This work was carried out in collaboration with colleagues from Imperial College London and University of Munster. So this is the outline. We're going to first talk about the motivation of this project, and then new discrete heavy-tail distributions that we aim to contribute to STEM math library. There are 3 new distributions plus a alternative parameterization. In fact, there has been a long history of requests for such kind of distributions in the STEM community. Then we're going to talk about the data we use, the model we've developed, and the results from the model. Finally, we'll talk about the related development works of this project. Okay, so the very basic idea behind this project is that if Poisson and negative binomial are too concentrated for the discrete outcome data on hand, what parametric distributions can we use, and what parametric distribution can we use in STEM? The real-world networks are known to be highly heterogeneous. Let me first introduce some concepts in the network theory. The first, degree. Degree is the number of connections of a node K, of a node in a network denoted by K. And degree distribution is the probability distribution of K denoted by Pk. Skill-free network where Pk follows the power law. And the alpha here is called skill-free exponent. Typically, it's between 2 to 3. Hubs are individuals with extraordinary many contacts. They can act as super spreaders in disease transmission. So here's a very nice plot from Barabasi. Depicts the relationships of nodes, degree distribution in the skill-free network, which is the purple line, and hubs. So now we know that modeling degree distribution is important. What is a suitable distribution assumption? If we look at the data, so the x-axis, we'll talk about the data source in a second. The x-axis is number of non-household contacts. The y-axis empirical PMF, empirical CCDF. So from the left panel immediately, we see 3 distinct features. First, it's discrete distribution, and then power law, and finally low degree saturation, which means in many real-world examples, the empirical degree distribution does not conform a strict power law when the degree is low. And from the right panel, we see that the MLE fit for the most widely accepted distribution, Poisson and negative binomial to the data. It's clear that they can account for the heavy tail of the data. A widely accepted choice is zip distribution proposed by linguist Zip based on his study of word frequency tables in corpora. Here's the probability mass function. And it's a simple discrete power law function with a skill-free exponent alpha plus a normalizing constant. So here's the plot of the probability mass function. But it's a 1-parameter distribution, and it's not flexible enough. So we propose to use beta-negative binomial. It's actually the purple line here. So it fits the data quite well. So it's proposed by Irwin, studied in considerable detail by Irwin and Zakalaki, under the name generalized variant distribution. So here's the probability mass function. It is a power law distribution when y is sufficient large and with skill-free exponent alpha plus 1. That's one thing I'd like to mention about the PMF is that the parameters R and B are symmetric. So if you switch them, the PMF stays the same. So this would cause identification problems in parameter estimation, especially if you're using MCMC, right? Okay. Okay, we will solve this identification problem by proposing a new parameterization of the beta-negative binomial distribution. So why using BNB? Okay, BNB is actually a generalization of a variety of distributions, which they're all well studied and widely linked to the network and graph theory. For example, if you look at the first line, so in the parameterization we proposed, if you set sigma equals to 0, you have negative binomial distribution, the alternative parameterization, and it can also goes to Poisson distribution, which is the degree distribution of random network. In the second line, the vanilla BNB, it can go to variant distribution and the Yosemite distribution, which is the degree distribution of the famous Barabasi-Albert preferential attachment model. So we have a lot of theoretical support to use beta-negative binomial, and this theoretical theory could also provide us a representation of the underlying social process, so that we are able to estimate parameter, quantify uncertainty, and compare goodness of fit. Like, remember the low degree saturation is actually explained by the parameter beta in the variant distribution. Okay, so this is the new parameterization we proposed. It's a BNB mu sigma gamma. So here's the transformation from the vanilla BNB. The very basic idea behind this new parameterization is that we want to convert the label condition, which is R is greater than B, to the domain condition, which is gamma greater than 0. And we also want all the three parameters to have real meanings, and the transformation is bijective. By proposing this new parameterization, we avoid label switching in M times C. So no need to manually process posterior samples. Okay, for sure, you can use the label switching packaging in R, but I'm a Python user, and I think I think it's always better to prevent issues mathematically before the sampler starts to work right. And we also have a tunable mean parameter, mu, the reciprocal of scale-free exponent sigma, and the dispersion parameter gamma, which allows to use the distribution regression technique, where you not only put linear predictor on the mean, but you also put linear predictor on the shape parameters. This is our data. We use COVID mode contact survey, which is one of the largest ever individual level longitudinal contact survey conducted nationwide in Germany. There were 33 weeks from April 2020 to December 2021, include more than 7,000 participants, and nearly 60,000 responses were collected. The survey method is through online questionnaire, including questions of demographics, household contacts, and non-household contacts, where contacts are defined as face-to-face communication or direct physical contact, like handshakes or hugs. Participants reported social contact over a 24-hour period. And this is what data looks like. The x-axis is participants' age from 0 to 85. Y-axis is the total number reported. A total number of reported contact by male participant at the specific age for lockdown period and relaxed measure period. So that it can be clearly seen that people changed their contact behavior with ages and time period. So our specific questions, that yi represents the number of non-household contact by respondent I, where the distribution of yi can be regarded as the distribution of the contact network. We're interested in two key parameters that summarize the network characteristics. First is mean of degree, mu I, and the next is tail heaviness, sigma I. We're interested in the evolution of the network in terms of age, sex variation, and spatial temporal dynamics. And we're also interested in presenting insight from correctly modeling tail behaviors by using BNB. This is our model. So it's a simple generalized linear model, like in the log of tail heaviness sigma I. The linear predictor, we put a baseline parameter, gender effect, wave group effect, geographic variation, and the interaction term of wave, gender, and age. The mean is basically the same, except for we add an additional parameter capturing the reporting fatigue effect. And we use 10 for numerical inference. So here's the results on the mean. The x-axis is participants' age from 0 to 85. Y-axis is mean of daily non-household contacts by male and female and 5 different restriction phases based on national level NPIs in Germany. It can be clearly seen that, like, for example, in first lockdown and second lockdown, the mean of contact and the age differences are smaller than other period. So this is our result for scale-free exponent. Here's the result: the 95% credible interval of the population level scale-free exponent. When the scale-free exponent becomes smaller, the tail of the distribution becomes heavier. So it can be seen that, like, during first lockdown, the estimated scale-free exponent is outside the scale-free regime, which means that the underlying contact network is not much different from a random network. But as time goes by, the contact network gradually recovers from a damaged state to a scale-free state. We call this the reemergence of scale-free property in human contact network. Then we investigated what is the absolute number of contributed by the tail population in different time periods. So here's the result. The black points are the data, and the color lines are from different posterior jaws generated quantity. The x-axis is people with top X% contacts in population. And the y-axis is contacts contributed by this group of people in the tail, but normalized to 1,000 capita. It can be like clearly seen that this increase from first lockdown to relaxed measures and the decrease. Okay, then we examine the 80-20 rules. 80-20 rules as like 80% of outcomes, in our case, contact behavior results from 20% of cases. This is the result of people with top 20 contacts contribute to how much of the total contacts. So the x-axis is a percentage. And I mean, by this, it's like the 80-20 rule is not an abstract concept. If we really quantify the numbers, it can be seen that as the tail of the degree distribution becomes heavier, this proportion becomes larger. Okay. Finally, robustness, vulnerability, and epidemiology. So the scale-free network are known to be robust to random attack, but vulnerable to targeted attack to the nodes which are in the tail. So we, from the posterior estimated degree distribution, we generate a synthetic network and remove nodes one by one from the synthetic network. After each removal, we compute the giant component proportion, epidemic threshold, this index of this network. We're using two strategies to move the nodes in the synthetic network. First, the targeted removal is plotted by solid line, and random removal is plotted by dashed lines. So the x-axis is the removed proportion from 0 to 1. And it can be seen that, like, in targeted removal, you just need to move a small fraction of points to make the giant component collapse. And at the same time, the difficulty of spreading epidemics in the network becomes increased dramatically. But in random removal, the giant component keeping exists. It's just its size becomes smaller and smaller, and the epidemic threshold not change much, at least in the log scale, until you remove almost all the points in the network. Okay, then we're going to talk about some development work. So I don't know if anyone have encountered this situation. The distribution I use is not yet included in STAN, or it's too slow with built-in automatic differentiation. I would like to contribute, but how can I do it? Well, I am a statistician or a C++ experienced developer. Well, you need to write a C++ template function, and we provide a detailed STAN case study. Based on this, we've implemented the two distributions we mentioned. It's a vanilla beta-negative binomial and the new parameterization of beta-negative binomial. Actually, the first one, the vanilla BNB, contains 2 more new distributions after simple wrapping. So we are working on pull requests. And another scenario is my data set is large, and there's big matrix manipulation. I want to use GPU to accelerate, but Stans OpenCL does not support the function yet. What should I do? I would say you could try using CUDA. You can actually move any part of the model to GPU, even the parts related to gradient. We have provided a detailed CMD-Stan CUDA example. In short, it's actually simpler than you think. So first, you move the calculation into the. It is, yes. When I wrote the code, I think it's hard. I think I should like take several days, but it only takes me like 1 or 2 days to achieve this. Okay, first step and second step, you compile the CUDA code and then add CUDA runtime to the linker. So here's a rough performance test. As we've mentioned, the current project has around 60,000 data points, and by GPU, it basically achieved 3 to 4 times speed up. Okay, here's a QR code for all of the code I've mentioned in the slides. You can find the repositories in this GitHub organization. Thank you. Any questions?
Say that the original parameterization has a twofold symmetry from swapping alpha and beta.
Yes, yes.
And that the transformation is bijective.
Yes.
Doesn't that mean the new parameterization also has a twofold symmetry somewhere?
Okay, you're right. So it's not fully bijective. I mean bijective is that if you is
it bijective except for the symmetry?
If you let R greater than B, then these two are bijective. Yeah.
You commented at the end about the speed up, but can you give a sense of like the just raw timing? Was this fit something that took days or hours or? Second. I see the axis.
Yeah. It's second. So it's just a rough performance test. Like you can see. So in my implementation, if the dataset size reaches here, which means the GPU and CPU performance are the same, and if it exceeds this point, you can use GPU.
But even the CPU was still minutes, not weeks or whatever, right?
No, never weeks.
Maybe one more question. Okay, so let's yeah.
I was just wondering quickly, I think that because of the elliptical distribution, do you have any experiences with distributions that are under dispersed rather than over dispersed? And if yes, do you have any recommendations?
Any experience of one? Can you?
Of under dispersed count distribution.
Sorry, I'm afraid.
Under dispersed, doesn't it?
Yeah. I'm afraid I have no experience of under dispersed.
So let's thank the speaker again.